So now we're going to work with determinants. We've already gone over inverses and how to calculate inverses using modern linear algebra. We'll now look at determinants. Now, determinants to some degree can be considered an old-fashioned way of calculating with matrices because a long time ago they were used to find all the things we now find with row operations. So in one way, we can say that they're obsolete, but in another way, they show up all the time. There are higher order math calculations that you will use in differential equations and beyond that require the use of a determinant in order to evaluate. So let's look at what a determinant is. In a 2 by 2 matrix, the simplest form, if you have A, B, C, D matrix, the determinant is really just A times D minus C times B, or B times C. That calculation in a 2 by 2 matrix, so that's A times D minus B times C. That's the calculation to find the determinant in a 2 by 2 matrix. Now, we know that we don't work only in 2 by 2 matrices, so we'll have to learn some more tools that are a little bit more sophisticated to find the determinant of higher order matrices. But let's start just by working with the determinant of a 2 by 2 and then use that to find the inverse of a 2 by 2. And I think it would be smart of us to use the matrix that we've already used. So we had matrix A, and we calculated using row operations to find the inverse of matrix A. So let's use determinants now to find the same matrix A. I'm going to write in a different color so we know that I'm talking about the new lesson. So I have -4, 3, 6, -5. Now, what I'm really going to do is try to find the inverse of A by first finding the determinant and then using an operation with the determinant to get to the inverse. So first, let's find the determinant of A. And there are a number of ways to write that. I can write the determinant of A. Shorthand is A inside of a double bracket, like absolute value, bracket of A. Or I could write the entire matrix inside of a determinant bars rather than inside of brackets. So all of these mean I'm looking for the determinant of A. All right, but we know that that is positionally AD minus BC. So let's go ahead and do that calculation then. So for this matrix A, the determinant of A equals -4 times -5, which is 20, minus 3 times 6, which is 18. So the determinant is just the number 2. Okay, we can work with that. Now, to find the inverse, using the determinant, we are going to multiply the actual matrix, well, not the actual matrix, don't let me get ahead of myself. We're going to take 1 over the determinant of A times this funny matrix where I'm going to do a flip and change the signs. I'm going to flip A and D. So remember when we set this up to tell us to talk about AD minus BC, the position was AB, C, D. And then we did this AD minus BC. All right, so with these positions, we're talking about the original matrix calculating the determinant. Now, once I find the determinant, if I want the inverse, I'm going to do some flippy things. I'm going to flip A and D. Right? So I'm going to flip D, put D where A was, and put A where D was. Then I'm going to leave C and B in the same place, but I'm going to make them both negative. Okay, so now that's the formula to give me the inverse of this original matrix A using the determinant to calculate the inverse. So that means the determinant then is 1 over 2, so 1/2 times the matrix, the new matrix, D, which the original D was -5, the original A, -4, the original C stays in the same place but changes signs, and the original B stays in the same place but changes signs. Now I just have a scalar operation. 1/2 times -5 is -5/2. 1/2 times -6 is -3. 1/2 times -3 is -3/2. And 1/2 times -4 is -2. And do you remember what the matrix was when we found it by row operations? Check it out. -5/2, -3, -3/2, and -2. Pretty cool, huh? Okay, well, so this is great for 2x2 matrices. And in fact, with the work I just did, you're probably thinking then, why on earth would we go through all of those row operations and all that craziness? But the truth is, as soon as matrices get bigger, even a 3x3, it's certainly doable, but calculating the determinant in the beginning is almost as complicated as doing a bunch of row operations, and so it gets more and more complicated. For larger matrices, using row operations is the better choice. For small 2x2 matrices, finding the inverse by calculating the determinant first and using the flipped matrix is perfectly fine. So one other way that a determinant is useful is it first tells you before you go through all the row operations whether you're wasting your time. So not all matrices are invertible. A matrix that cannot be inverted is called singular. And so a determinant gives you a shorthand way to determine whether or to figure out whether or not a matrix is invertible. So if I were to take this matrix, -4 times -12 is +48, and -8 times 6 is 48, I end up with a determinant that equals 0. But look at the calculation we're going to use. We're actually going to put the determinant into the denominator of a scalar to multiply with the flipped and opposite matrix. Well, that's crazy. We can't put 0 in the denominator, and that means that this matrix is not invertible. It is a non-invertible matrix, and it's called singular. Okay, so if you can calculate the determinant before you go through a whole bunch of row operations, it's pretty convenient. All right, so let's look at a process for calculating the determinant of a matrix that's not a 2x2. So we already talked about how those are a little bit more complicated. So all right, so this is number 7 in your textbook, and they chose to do a different row that I'm going to. They used the first row to evaluate this, and I figure it's probably meaningful for you to see it worked in 2 different ways, and since it's possible with this example, that's why I've chosen it. So the determinant of A, in this case, is a formula. So what they did is, well, let me write it out first. So if you have, for example, a 3x3 where you have A, B, C, D, E, F, G, H, I, okay, you can choose any row, or any column. So if you've got a column with a 0 in it, I would have probably chosen either the 3rd column, and I probably will, or the 3rd row, because the 3rd row has really little numbers in it, and it has a 0. But I'm sure they just wanted you to see every step of the process. That's why they chose the 1st row. Then you're going to use each element of the 1st row and whatever makes up the determinant inside. So that made no sense what I said, I know. Let me show you. So you're going to take A and you're going to multiply it by the determinant that remains. If I use A, then I'm going to mark off that row and that column, and whatever's left, I'm going to calculate the determinant of E, F, H, I. Then I'm going to subtract, it's plus, minus, right? So I'm going to subtract B. Now this time, since in this term I'm using B, I'm going to cross B out. A is already crossed out. And so then I'm going to calculate the determinant of DGFI. Plus, remember, plus minus plus. C times, by the way, I just had to go away to sneeze. I'm doing this while I'm sick, and so I have to keep pausing for coughs and sneezes. If it's very herky-jerky as a video, I apologize, but that's why, if things cut out and cut back in a funny way. So C times the determinant D, E, G, and H. All right, so just a bunch of calculations. And your textbook did row 1 to make these calculations. I'm going to use row, well, I think it's probably useful for me to go ahead and use row 3. Well, I think I'll use column 3 to show you that it works with a column, and it doesn't matter if you 0 1 out. I will get the same value as your textbook. So let me look ahead and see what the textbook got for this one. So your textbook's operation said that the determinant equals 32. And then we'll calculate the inverse from there. So let me use my calculations then. I'm going to say that the determinant of A equals my first element 4 times the determinant created by marking out the row and column that include 4. So I have 1, -1, -1, and 4. Minus plus minus 2 times, this time, the determinant of what's remaining after I cross off the row and column that include 2, -3, 2, -1, and 4. Plus 0, but 0 times anything is just 0, so I'm done. So if I do my math, then I get 4 times, well, the determinant is AD, so that's 4 minus -1 times -1 is a positive 2, so 4 minus 1. Minus 2 times -3 times 4 is -12. Minus 2 times -1 is -2, which is a plus 2. And so I get 4 times 3, 4 minus 1 is 3, times 4 is 12, minus 2 times, well, -12 plus 2 is -10 times 2 is -20. So 12 plus 20 equals 32, and that's exactly the same value the textbook got using a different row and column. So now the instructions were to first find the determinant and then find C inverse if it exists. So the if it exists part we've already figured out, right? Because since the determinant does not equal 0, then we know that A inverse exists. So let's find it. Well, wouldn't it be lovely if we had a really nice way to flip our original matrix like we did up here and calculate our inverse by multiplying, using the determinant, the inverse of the determinant, as a scalar multiple of the flipped and negative matrix. But that doesn't exist for a 3 by 3 or greater matrix. And what your textbook does is goes on to give a lesson in using the graphing calculator to solve a matrix. And so I'm going to use my graphing calculator and show you what yours can also do. If you don't have an 89, that's okay. You just have to Google how your calculator does or solves a matrix. So I have a TI-89, a very, very old version of it. I'm sure you have something newer if you have a graphing calculator. If you have an Inspire, it'll give you a template to fill in. It's super easy to use. If you have any of the other 83, 84, whatever, just Google how to do it. So for the 89, the way I would enter a matrix is I would use these brackets here. So you can see the gold button is going to give me a second function bracket. So I choose the bracket. And then I actually want two brackets. There's a enclosing bracket for the whole matrix, and then there's a bracket for each row. So now I'm going to second function for my next row. My first row is -3, 2, and 4, and I'm going to enter those values with a comma in between. Now I'm going to close my bracket and then open the next row, which is 1, -1, 2. Comma, sorry, I got hung up. -1, comma 2. Close the bracket. 1, -1, 2. Yep. And now I'm going to open up for my third row, -1, 4, and 0. -1, comma 4, comma 0. And now I'm going to close that row, and I'm going to close the entire matrix. And I like to enter it that way just to see that I've entered it correctly. -3, 2, 4, 1, -1, 2, -1, 4, 0. So I've done it exactly correctly. Now I can do work with it. First thing I want to do is I just want to do reduced form, right? I just want to look for row echelon or reduced echelon form. So I'm going to open up my catalog, and I'm going to choose the letter R because it'll get me in the R area of my catalog. And I want reduced form. So here I've got REF, and there would be another one for RREF, which is my calculator's shorthand. Hang on, let me find it. This print is really little for me. They're RREF. So this would be Gaussian, Gauss-Jordan elimination, upper and lower triangle, and REF would be just lower triangle, REF. But I don't have to actually do operations on it. If I wanted to use, I just wanted to show you where those buttons were. If I wanted to use reduced and row reduced forms, then I would have to have put together the augmented matrix like I had here, where I started with my matrix, and then for continuing my row, I would have to put the identity matrix and ask it to reduce or put it in reduced row echelon form. But what I really want to do is just find the inverse. And so I can find that. Let me escape out of here by just treating this like it was a number. So if I wanted the inverse of 2, I could raise 2 to the -1. And that gives me 1/2 as the inverse of 2. I can do the same operation then with my matrix. So I can just say, I can go up here. I'm going to keep that there. Let me put my caret in so it's still there. So I'm just going to go up and copy my matrix and have it raised to the -1. Copy it in here. So I have my whole matrix. And at the end of my matrix operations, I've got raised to the -1. When I enter, it tells me right here, my matrix to the -1 is equal to this matrix. And sorry if things just jumped around on you. I got a little glitchy on my end. So I'm not going to read the elements. This is the same matrix that your textbook found. So here's where we are. We have inverses and determinants of matrices. Inverses, super important. We're going to use a lot in the next few days in particular and over time. You should be able to calculate an inverse by converting a matrix joined together with an identity matrix and row operations. You should be able to calculate the inverse of a 2x2 matrix using the determinant method. And then you should be able to always calculate the determinant of any size of a 2x2 or a 3x3 using the two methods I've shown you here.